Uh, Good evening, everyone. To all those who are joining today for the first time, my name is Akhil. I'm currently a PhD scholar in the Department of Mechanical Engineering in IIT Madras. So we'll have this weekly sessions where I solve some of the problems similar to your assignments every week for the course Machinery Fault Diagnosis and Signal Processing. We'll have these sessions every week from Saturday 7 to 9 p.m. 2 hour sessions. And I request all of you to mute yourself as default. And whenever you have a question or doubt, you can unmute yourself and ask. Okay. And these sessions will also be uploaded in YouTube. Mostly, you will be finding them tomorrow afternoon or something like that. Sunday afternoon. And these notes will also be shared with you. So in YouTube, if you search for this as machinery fault diagnosis and signal processing playlist, you will find it. You can also search by my name, Akhil Reddy. Okay. So yeah. So this week we'll be solving some of the problems similar to your week 3, which you need to submit the coming Wednesday. Okay. So yeah, let's begin the session. So the first question: what is the amplitude and time period of the signal, which is given as x of t as a function of time? 6 plus 3 sine of 60 plus pi by 4. So can anyone tell me what would be the amplitude? Anyone? What would be the amplitude of this signal? Okay. Uh, yeah. So let's try to look at this signal. One simple thing that you can do is just actually plot the signal as a function of time. Okay. So if time is 0, this is x-axis t and this is x, and let's make it this is 9 and this has 6 and this has 3. Okay. So at time 0, what would be the value of x? So it would be just a 6 plus 3 into sine of pi by 4, right? As t is 0, so it would be 6 plus 3 into sine pi by 4 is 3 by root 2. Okay. Now at t is equal to pi by 4, what would be x? 6 plus 3 into sine of uh, okay, so 6 pi by 4 plus pi by 4. So 6 plus 3 into sine of 7 pi by 4. Okay. So this would actually be pi plus 3 pi by 4. So 6 plus 3. Sine of pi plus, what would be sine of pi plus? So it would be minus sign, right? So this pi by 4 would be again 6 minus 3 by root 2. So to look at in between values, we can try one more case. T is equal to, if we try pi by 12, so we will get pi by 2 plus. So So let's try t is equal to pi by 6 into 1 by 4. This would give 6 into pi by 6 into 1 by 4 plus pi by 4. So 6 gets cancelled. So 6 plus 3 sine of pi by 4 plus pi by 4. So 6 plus 3 sine 90. So it would be 1. So 9. So if you do like this, because this is sine wave, you would actually get something like this. And initially it is 6. So it is starting somewhere above 6. So and at pi by 24, it would reach 1. It would reach 9 here in this case. So this is how this wave should look like, right? Because the maximum of sine is 1. Maximum of this value would always be 1 and the minimum is minus 1 if it is a sine function. Is that correct? So the x of t maximum would be 6 plus 3 and the minimum would be 6 minus 3. So between 3 and 9. And hence, if you are looking at the amplitude, is the maximum minus minimum by 2. So it would be 3. Okay. So the existence of this constant doesn't affect the amplitude. Whatever value is the coefficient for sine, that would be the amplitude. Okay. So the amplitude is 3. And if you want the time period, so whatever is the coefficient of t, that is what you should be looking at. So it is given 60. So if it is a sine function, usually whatever this 6 corresponds to omega, and that is in terms of the frequency can be calculated this way, 2 pi f. Okay, so the frequency would be omega by 2 pi, in this case 6 by 2 pi. Okay, so is this clear? So if you have a general sine wave, so this would be the frequency in radians, and if you want the actual frequency, you need to convert the frequency in radians to the real frequency. Okay, so this radians per second, and this would be 1 by second, hertz. Okay, and b would be the amplitude, and phi would be the phase, and this is constant. So this will change where the sine would look like. So this 6 actually decides above which point the sine wave starts. If this constant is 0, then this sine wave would be about 0. Okay. So this is how you can estimate the frequency and the amplitude. So whatever is the coefficient of the sine or cos, that becomes the amplitude, and whatever is the coefficient of t, that becomes the radial frequency, and from that you can actually estimate the real frequency. Okay. So is this clear? Is this question clear to everyone? Abid, is it clear? Yeah. Okay. Okay. Thank you. So this is how you can estimate amplitude and frequency. Next we'll see different questions. Yeah. So what are the values of mean, maximum, minimum, RMS, crest factor and form factor for this signal. So can anyone tell me what should be the at least mean, maximum and minimum for this cos wave or the cos signal? First, let's say what would be the maximum? Anyone? Okay. So the maximum of cos is 1 again, and the minimum would be -1 for a cos function. Okay, so the maximum of this would be 10 into 1, 10, and the minimum would be -10. Okay, so what would be the mean? So for sine and cos without any constant term, mean is always 0. And how can you estimate the RMS and crest factor and form factor? So let's see if we have any general signal xi, uh, some data points x1, x2, x3. So this is a general signal. Till we have, let's say, n number of data points. If that is the case, so what will be the mean? X bar sigma xi by n, right? So this would be the mean. Minimum and maximum, you know how to do. Just max of and then minimum. Now, what would be the range? Range would be x maximum minus minimum. And what would be the RMS? So the RMS for this data set would be, so basically RMS means root mean square. So first you do the squares of the data. So you do the squares. So x1 square, x2 square, x3 square, so on, and then mean them. So sum up all of them by number of data points. So that is the mean, and then square root of that. So that is what RMS means. Root means square. Okay. So now what is the RMS for cos function? So usually RMS for any sine or cos of form A sin omega t or B A cos omega t would be A by root 2. Okay. Okay. So RMS for any sine or cos would be A by root 2 only. So we can also actually derive it. So let me simply show you the derivation once so that it gets clear how exactly that by square root 2 come. So I is equal to 1 to infinity x I square. So let's look at a sine wave. Yeah, sorry for that. Yeah. So let's look at sine wave from 0 to 2 pi. So sine 0 is 0 and sine of 2 pi would be again 0. Sine of pi would be 0 and sine at pi by 2 would be 1 and 3 pi by 2 would be -1. Okay. Now, let's say if you have such a data, now we need to do the mean of squares. Okay, so xi would be my a sin ti. Okay, now if you are converting it into time domain, then we can actually integrate this instead of doing the sum up. So then we can write this as, so because we are deriving from 0 to 2 pi, we can just do this. Okay, so this would mean a square by 2 pi integral 0 to 2 pi sin square ti dt. Okay, so what would be the integral of sine square? So we don't directly know for sine square, so what we can do is we can convert it into cos. So sine square you can write it as 1 minus cos of 2t dt. So then this becomes, so what would be the integral of cos? It is sine. Okay, so root over a square by 2 pi. So if you substitute 2 pi minus 0, t would be 2 pi minus sine of 2 into 2 pi minus sine of 0 by 2 is total by 2. So sine of any number into pi is 0. Sine of 0 is 0. So you will actually only have a square by 2 pi into 2 pi by 2. So only pi. So pi also gets cancelled. So you will only have a square by 2. So which is a by root. Okay. So this is how, if you have any sine or cos, you will actually only have a by root 2 as the RMS. Okay. So for this case, what would be the RMS then? So amplitude is 10, so you will have 10 by root 2 as the RMS. Okay. Now, what would be the crest factor? So crest factor is defined as the ratio of maximum to the RMS. So maximum here is 10 and RMS is 10 by root 2. So the crest factor is root 2. Okay. And what would be the form factor? So the form factor is defined as RMS by mean. Since the mean is 0, form factor becomes infinite. Okay. So for sinusoidal wave or cos wave, the form factor in this case always becomes infinity because the mean is 0 if it is just a pure sine or cos. And the crest factor, if it is pure sine or cos, then it would be just root 2 always. So this you can remember. So the crest factor is defined as maximum by RMS and form factor is RMS by mean and RMS is amplitude by root 2. Okay. Yeah. Any doubt in till here? These two questions? Okay. So let's move on. So the third question If the amplitude is decreased to half of its original value, how will the mean, maximum, minimum, RMS, STD and variance change for a time domain signal? Okay. So what they did was they changed the amplitude to half of its original value. So if they change the amplitude to half, so let's say if our signal is A sin omega t, then if they reduce the amplitude to half, uh, so this would be your new wave, right? A dash by 2, A by 2 with the amplitude. Now if we have that, then all the data points would also become okay. So let's call it a new signal y. So if original data is x1 to xn, the new data would be x1 by 2, x2 by 2, x3 by 2 and so on xn by 2, right? So if amplitude becomes off, all the data would also become 1 by 2. Now if we change the mean, so mean is sigma xi by n, right? So sum of all the data by total number of data points. So for the new system, sigma yi by n, but yi is became xi by 2, right? So 1 by 2 into sigma xi by n. So 1 by 2 into original mean. So the mean becomes actually half of the original value. Okay. What about the maximum? So the amplitude becomes half. The maximum should also become half, right? So half of original. What about the minimum? Again, it would also become half of original. So these are the cases if it is a pure wave. But if it is like some constant, then this would be not exactly the same. Okay. Yeah. So mean, max, min. What happens to the RMS? So RMS also sigma xi square by n, old RMS. So new RMS would be square root of sigma yi square by n, square root of sigma yi is xi by 2 whole square by n, x square by 4 and so it becomes 1 by 2. So 1 by 2 into old RMS. Okay. And finally, what would be the variance and standard deviation? So the variance of a data, you can estimate it as okay. So the variance for given data in terms of the data points and the mean, you can estimate as sigma sum of the difference squares by the total number of data points. So this is for x. For y, the variance would be but yi is xi by 2 and we saw that mean also became half of it. So x bar by 2 whole square by n. So if we take that 1 by 2 outside, so then it can becomes 1 by 4 xi minus x bar whole square by n. So this makes it 1 by 4 into, so this is the old variance, right? Okay. So let's say if this is for this, then sigma 2 of new data would be 1 by 4 of variance of the old data. So the variance, if you reduce the amplitude by half, variance reduces by 4 times. Okay. Then what about the standard deviation, which is sigma? So if you do the square root of above, so the standard deviation reduces by half. Is this clear to everyone? So what will happen to the mean, max, min, RMS, standard deviation and variance when you change the amplitude of the time domain signal? Okay. Yeah, I hope this is clear. So if you reduce the amplitude to half, mean also becomes off, maximum becomes off, minimum becomes off if it's a pure time domain signal, and the RMS becomes also off, and the standard deviation becomes off, and the variance reduces by 4 times. Okay. So next, look at a different question with a similar this thing. If you do a negative offset is given to a time domain signal, its variance. So what is the formula for the variance? Sigma square is equal to sigma xi minus x bar whole square by. So if this is the variance and a negative DC offset, that means you are changing xi with old xi minus some constant delta. So if you do that, what will happen to the mean? Mean will also reduce by delta, right? Because you are changing all the data points, your new mean would also change. So what would happen to this equation? Sigma square of the new data would be, now your xi is xi star minus x bar star by n, but xi star is xi minus delta, so xi minus delta minus x bar star is x bar minus delta. Okay, then xi minus delta minus of x bar minus delta, so xi minus delta minus x bar minus of minus plus delta whole square by n. So you see minus delta and plus delta is gets cancelled. So at the end you again have xi minus x bar whole square by n, which is same as sigma square. So when you change the values, when you add or subtract something to the existing data, the variance doesn't change. Okay. So remains the same. Is this clear? Yeah. Any questions till whatever we have discussed it till now? Okay. 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 Thank you. So I hope others also don't have any questions. If you have any questions, you can unmute yourself and ask. Okay, so let's move on to the next question. Skewness. So does anyone know what does skewness represent? Any idea? Okay. So here we have two curves. So one graph looks like most of the data is towards the right, most of the data, and one graph has most of the data towards left. Is that clear at least? Because here, yeah, most of the data is towards right, and here most of the data is towards left. So this skewness actually tells you is a measure of the symmetry of the graphs. So if the graph is perfectly symmetric, then the skewness would be 0. Okay, a perfect symmetric graph doesn't have any skewness. And the way to estimate this skewness, if you have a data set, is the following form. So this is the formula to estimate a given skewness for a given graph. Okay. Now, if the graph is towards right, so if you see this graph looks symmetric, right? But these two are not symmetric. So they will have non-zero skewness values. And if the data is towards right, that means right skewed, then you will actually have negative skewness value. Okay. And if data towards left, left skewed, then you will have positive skewness value. Okay. So this way, based on the skewness, you can actually comment on what is the kind of shape of the distribution. Okay. So if the skewness is positive and higher, then higher and higher values means it is more and more skewed to one side, and positive means it is skewed to the left, and negative means it is skewed towards the right. Okay. And this is how you can actually estimate what is that exact skewness for a given value, and sigma is the standard deviation which you have seen in earlier case. Okay. And here if you notice the order is 3. Okay. And there is one more thing called kurtosis. So we will see that in the next question. So that also tells you something about how the data is. Is this clear about the skewness? So skewness tells you what kind of graph it is, either it is symmetric or asymmetric, and if it is asymmetric, which direction it is asymmetric about. Okay. Yeah. So the next we have kurtosis. Yeah. So the kurtosis yeah, indicates the heaviness of tails. So this basically means if there are extreme values or not, on how much extreme values are there. Okay. So kurtosis, the formula is, so here the power would be 4. So for skewness, the order is 3 in both xi minus x bar whole power 3 and sigma power 3. And in kurtosis, xi minus x bar whole power 4 and sigma power 4. Okay. And Yeah, indicates how heavy the tails are, and if it's a perfect normal distribution, kurtosis value would be 3, and if it is more, if you see the red graph, so you can see that the data, like there are extreme values. So let's say this is 0. Compared to its distribution, there are more extremes on both sides. So this is called heavy tailed, and this will have positive kurtosis value. Okay. And if you see the blue one, compared to the distribution, the tails are not that much. There are less tails. So this will have negative kurtosis value, and this would be low tail. Okay. So is this clear? So the kurtosis indicates the heaviness of the tails, and that means let's say most of your data is between 5 and minus 5, but there are some data points at 10 and minus 10, 12 and minus 12. Compared to that, your data, second case, where all the data lies between 5 and minus 5. So the first data which has points at 10 and minus 10 is heavy tail. So that is why it will have positive kurtosis compared to the other one. Okay. So this kurtosis indicates how heavy the tails are. Is this clear? So if the tails are big compared to the data, then it will be positive kurtosis and heavy tail. And if the tails are less, then it would be negative kurtosis and low tail. Okay. So as skewness indicates the symmetry, kurtosis indicates the tailed behavior. Tail behavior. Okay. So let's look at one more question. So if you have seen the Sir's lectures, he would have gone through Fourier series expansions of any time domain signals. So this is one question from such questions. So Fourier series expansion of a periodic odd function. So odd function means if you take negative of the same variables, you directly can get by negative of the full function. Okay. So odd function negative x would be just directly negative of the full function, and even function okay. So for example, let's look at f of x is equal to x square. Okay. So when x is 0, why this is f of x is also 0. When x is 1, f of x is 1. When x is minus 1, then also you will have, so x is equal to 0, f of x is 0, and x is equal to 1, f of x is 1, x is equal to minus 1, then also f of x would be 1, right? So if you actually plot the entire function, then you would get something like this. So here if you see about the y-axis, this graph is symmetric. So that is an even function. Okay. But let's say if you are looking at only f of x is equal to x. So x is equal to 0, f of x would be 0. When x is equal to 1, f of x would be 1. When x is equal to minus 1, f of x would be minus 1. So this is minus f of x, right? So this is an odd function. And if you plot this, So fx is equal to 1 and x is equal to minus 1. So you would have something like this. Okay. So this is what odd and even function means. Now, what exactly does the Fourier expansion do? So a general Fourier expansion would be about t if you write. This is a generic Fourier expansion I am giving. Okay. Now, so if it is an odd function, then if you take the negative x, then you can directly should be able to estimate by taking the negative of the full function, right? So let's see what f of minus t looks like. So a naught by 2 stays as a naught by 2 plus cos of n equal to 1 to infinity a n cos. So t is minus t, so minus n omega naught t plus bn sin of minus n omega naught t, right? Now cos of negative is positive only. So cos of minus x is cos of x, but sin of minus x is minus sin of x. So this would become minus sin n omega naught t. Okay. Okay. Now if it is an odd function, then f of minus t is equal to minus f of t, right? So if we write that f of minus t is a naught by 2 plus an cos n omega naught t. So I am dividing the summation. So minus bn sin n omega naught t. This is equal to minus f of t. So minus a naught by 2 minus an cos n omega naught t minus n is equal to 1 to infinity bn sin n omega naught t, right? So I'm basically writing the minus of the full f of t. Now if you see, here you have positive a naught by 2, here you have negative a naught by 2. So if a naught exists, then this condition won't be satisfied, right? So in your function a naught term shouldn't be there, and similarly if you look at the cos terms, here they are positive, here they are negative. So if you have cos in your function, then this odd function condition won't be satisfied, so you shouldn't have cos also. So if you have only sine, then it is same on both sides. So if Fourier series has only sine terms, then f of minus t is equal to minus f of t. That is odd function satisfies. Is this clear? Now if it has to be an even function, then f of minus t would be f of t. So that would actually give cos term should be present, and if you have sine terms, then you won't have that even function. So then you should only have Is this clear? How I did this? How to see which terms will be present if you want odd and even? Is this clear? Yeah. So I just substituted minus t, and in the final function I compared the terms on both sides. If it is an odd function and then even function. If the terms are not equal, exactly same, then those terms shouldn't be there. Whatever terms are exactly same, they can be there. Because if they are exactly same, that means you are satisfying the condition. Okay. The other terms if you remove, then you are satisfying the condition. So whatever exist remaining terms, only those should be present. So for odd function, the terms are to be sine terms, and for even function, if you do, you'll see only cos terms should be present. Okay. Yeah. So I hope this is clear for regarding the Fourier expansion. Now let's look at the next question. Yeah. So a new signal is formed by combining two signals of very close frequencies. Here 10 and 12 hertz, and the resultant signal looks like below. So this is called the phenomena of beating. When you have very two close frequencies and you combine them, you will have a new signal which looks like this. And for this case, what will be the beat frequency? Anyone has any idea about the beat frequency? So the beat frequency is just the difference between absolute difference between the two frequencies which you are combine. Okay. So in this case 10 minus 12, so the beat frequency would be 2 hertz. Okay. So when you are combining two signals of very close frequencies, then you will get this new phenomena, signal beating, and the beat frequency would be just the difference between these two signals. Okay. Yeah. I hope this is clear in this question. Now let's move on to the next question. So digitizing the data. So yeah, in reality you'll actually have continuous data, analog signals, but when you want to track that data and store it, you'll actually be able to track whatever or detect at some given time steps. So that is the sampling interval, the difference between the time steps at which you can actually detect something. Okay. And this frequency would be the sampling frequency, and in a given time how many number of data points to n, and the total time length t, frequency resolution f, and maximum frequency would be f max. Now in certain way these terms would be related to each other. So the total time is basically number of data points into the sampling interval, right? So you're sampling every, let's say, 1 second, and you took for 100 data points, then the total time would be 100 seconds. Okay. Now the frequency resolution would be 1 by total time. Okay. So the difference between two frequencies, when you actually convert this into Fourier transform, the resolution which you can get is the inverse of the total time length which you have took the data. Okay. And sampling frequency would be just the inverse of the sampling time interval. Okay. And yeah, and the maximum frequency that you can get from this kind of sampling would be n by 2 into f. Okay. So n is the total number of data points you collected by 2 into the frequency resolution. So this is the maximum frequency that you can obtain, because when you do a Fourier transform for a given signal, you will get positive frequencies and negative frequencies, and you don't consider the data in the negative frequency range, you only consider the data in the positive range. So you'll only end up with half of the total considered size. So you'll have only n by 2 into f. And in reality, in the real situations, actually, only n by 2.56 f is considered. So it would be actually even more reduced. Okay. I hope this is clear. So how the total sampling interval details related to the sampling frequency and the total number of data points to the total time length and the frequency resolution and the maximum frequency that you can calculate from this data. Okay. Yeah, this is one example of how you will get the data. So there is a mistake here. So this is the x data as a function of time. You are looking at total time period of n into delta t. And once you did the FFT, in the positive spectrum, you can only get till n by 2.56 is what you can actually consider the maximum frequency that you can see. Okay. Yeah. Yes. So when you actually do this FFT, you would get some real component and some imaginary component. So here this one, you have some time domain signal and you did the FFT, then you get frequency function. Okay. So for this case, this frequency looked like 3 plus 4. Now we are asked to estimate how is the auto power spectrum is will be. Does anyone know what is the auto power spectrum? Okay. So first let's look at just this frequency, this thing. So as I said, there will be some real component and there will be some imaginary component. Okay. Now what will be the total magnitude? X real square plus x imaginary square. Okay. Yeah. Okay. So if it is new for you, you can maybe learn from this session what would be this Fourier transform and all this, and you can actually follow Sar's lectures also, where he has discussed what exactly does Fourier transform do. So Fourier transform is basically, yeah, any type of function which you have, any periodic data, you can write it in terms of a series of cos and sine functions. So that's what Fourier actually tried to establish. So that this final this free time response, if you write in terms of any sine and cos data, and then convert it into frequencies. So basically this n omega naught are the frequencies. So if you represent this in terms of frequencies, then that is called the Fourier transform. Okay. So when you do for a given signal the Fourier transform, you would have some real component and some imaginary component. Okay. So that is what from that real and imaginary you can estimate auto power and coherence and other cases. So we will see one by one in this session. Okay. So the magnitude would be just a root of squares, sum of the squares, and the phase of this Fourier or the signal would be, okay. So tan inverse of the ratio of imaginary by real component. Now the auto power spectrum So before going to auto power spectrum, there is one more thing which I should tell you. So this is the signal. Now there is something called conjugate. So defined as x star of f. So the conjugate of this signal is, so the imaginary component you actually take negative imaginary component or the opposite. Let's say you have x of f as x real plus I into x imaginary. The conjugate would be x real minus I into x imaginary. Uh, yeah. So in FFT and STFT, the main difference is the times with which you can do. Let's say you have a signal, or I will come to it after I explain this question, Muthu. So you have real component and the conjugate component. In the auto power spectrum, you multiply the real component with the conjugate component, the actual function into the conjugate. So if you do that, then x real plus I into x imaginary into x real minus I into x imaginary. So this would get x real square plus I into x imaginary into x real minus I into x real into x imaginary minus I into I square x imaginary square. Okay. Now if you see, these two terms are same, x I into x imaginary into x real, I into x real into x imaginary, so it gets cancelled out, and minus I square, so I square is minus 1, so minus of minus 1, so it becomes plus 1. So this is the auto power spectrum. Okay. So in this case, you have x real, you have the x of f given as 3 plus 4i. So the x real is 3 and x imaginary is 4. Okay. Now the auto power spectrum would be x real square plus x imaginary square. So 3 square plus 4 square. So 9 plus 16 is equal to 25. Yeah. Yeah. So now let's see some questions asked. Yes, the recorded video sessions will be given in the YouTube as I told in the starting. These notes would also be provided to you. So if you search for machinery fault diagnosis and signal processing live sessions in YouTube, you will actually can see these videos. There'll be this video, every session will be on Saturday. So mostly by Sunday afternoon, these sessions will be uploaded. Okay. And the notes would also be uploaded. Yeah. And coming to the question of Muttu, the difference between FFT and STFT. So in STFT, what you do is, in FFT, you do the frequency conversion for the entire data. So let's say as a function of time, you have this data, you do the FFT of the entire thing at once. Okay. In STFT, what you do is, okay, you cut the data into two different data sets and then do FFT on each of them separately. So that is STFT. Okay. So when you do full FFT, some different frequencies if you have, you might not be able to see them very clearly. In that cases, STFT is better. That means if the signal is changing, like let's say for the first 10 seconds, uh, yeah, let's say for the first 10 seconds it behaves like 10 sin 10t, and for the next 10 seconds it behaves like 2 sin 5t. So the signal behavior changes as a function of time. Then this STFT helps better. Okay. Is your question answered, Muthu? Is it clear now? Okay. Yeah. So now let's move on to the next question. So, so this is how you can estimate the auto power spectrum. Now let's see the next question. Yeah. So now when you have two different signals, okay. So this could be like you can imagine this is the input which you are giving, and this is the output you got. Okay. Now if you have two different signals, you can estimate something called cross power spectrum. So this kind of tells you how these two signals could be related. Okay. Now this cross power spectrum for these two signals, you can estimate in this manner. So you see what I did there. So for Y, I took the correct signal, but for X, I am considering the conjugate of the signal. So this is basically so 2 plus 3a into 3 minus 4a. Okay. So if you do the cross power for these two, 2 into 3 6 plus 9i, so minus 8i. So again 3 4s are 12 minus 12 I square. Okay. So 6 plus 9 minus 8 1 9. So plus I square becomes minus 1. So minus of minus plus 12. So 18 plus I. So the cross power spectrum is this. Okay. So you notice that cross power spectrum has still some imaginary components. Okay. So this is the cross power spectrum. And next, yeah, there is something called coherence function. So this, as we said before, if this is your input signal and this is your output signal, so this coherence function, I will tell you how it is defined, can tell you how these two are very correlated. So let's say you are giving some signal x of t, and for the full system, and there are two of your outputs, okay, y1t and y2t. Now this correlation function or the coherence function can tell you how much these x and y are related to each other or correlated. So let's see how this coherence function can be estimated. Coherence function is denoted this way, gamma xy square. So you notice the terms here. So this is the cross power spectrum, and these are the two auto power spectrums, right? And here you are looking at the magnitude of the cross power. So for these two, if we calculate, so first let's look at calculate the cross power spectrum. So first you take the 2 plus 3i into 3 minus 4 because complex conjugate y of it into complex conjugate. Okay, so I think this is same as our earlier case. Yeah, so this would be 18 plus I. What would be the magnitude of this? So root over 18 square plus 1 square. So whatever this comes out to be, square root of 325. Okay. Uh, now what would be the auto power function of f? Square root of, for x it would be 3 square plus 4 square. So, yeah, 3 square plus 4 square. So this would be 9 plus 16, 25. And for y you have 2 plus 3. So 2 square plus 3 square. So 4 plus 9, 13. So now the coherence function in terms of cross power and the auto powers. So the cross power square is 325 by 25 into 13. Okay. So is this clear? How can you estimate the coherence function? So larger coherence tells you that these two are very closely related. Okay. And a smaller coherence value tells you that they are not related at all. Okay. So now when you have two signals, by looking at x y1 and gamma x y2, by looking at these two values, you can tell on which the input has more or which signal is related correlated to the input more than the other signal. Okay. Yeah. So any doubts till the point which we discussed in this class? So we started from how can you define the amplitude and time period if a signal is given, a sinusoidal or a cosine signal, and from there we went to, so if a general sine and cosine signal are there, the amplitude is the coefficient of sine or cos. Yeah, thank you. And the time coefficient of time period would be the omega, frequency in radians. Now that you can actually convert to the real frequency by omega by 2 pi. Okay. So this is how you can estimate amplitude and frequency if a signal is given. And next we looked at how you can estimate mean, maximum, minimum, RMS, crest factor, form factor if a signal is given. So the main things to remember are RMS would be amplitude by root 2, and the crest factor is the maximum of the signal by RMS, and the form factor is RMS by mean. Okay. So if it is a sine or cos, only sine or cos, then the mean is 0. Because of that, form factor would always be infinite for sine or cos, pure sine or cos. Okay, I'm talking about pure sine or cos like this. And if you look at the crest factor for pure cos or sine, this would also be always constant and will be square root of 2. Okay. Now if you have a different signal, this crest and form factor you need to estimate from estimating the maximum RMS and okay. Yeah. So next, yeah, we also derived how that by root 2 comes for the RMS. Okay. Next, yeah. So next we looked at if you are changing the amplitude, how will the other values change? So the mean, maximum, minimum and RMS which you have seen here, these are only if it is a pure sine wave, okay, in this case only. But let's say a constant is there for the signal itself and then you are multiplying, then you need to put the correct case and then see how the change, okay. Yeah. So we also looked at how the variance and standard deviation also change. So for the variance, there is one more interesting thing. So even if a constant is there, the variance doesn't matter if a constant is there to the sine or cos. Okay. So for the variance and standard deviation, if you change the amplitude, then you don't need to worry about if a constant exists or not. You can directly see based on how much you are changing the amplitude, that many square times the variance gets changed. Okay. So if you double the amplitude, variance gets doubled and the standard deviation variance gets 4 times more. Okay. So and you can derive that this way if you know how the y and x are related. Okay. And these two are for you are doing the amplitude by 2. Okay. And if you are adding a constant as we saw and I told you earlier, the variance doesn't change. So if you are adding a positive or negative constant to the existing data, the variance remains same because variance tells you how the data is distributed. So for this, it doesn't matter where the data is distributed. So that means, let's say data is like this. If this is distributed about 0 or 10 or 100, doesn't change the variance of the graph. Okay. Yeah. Next, we look at the skewness. And the skewness tells you the shape of the graph or how symmetric it is. And if it's perfectly symmetric, skewness would be 0. And if it is the data is skewed to the right, that is most of the data is present on the right like this, then it will be negatively skewed and asymmetric. And if most of the data is towards the left, then it will have a positive skewness value. Okay. And the skewness can be estimated this way. So x minus x bar, which is the mean, whole cube, the summation of this by n minus 1 into sigma cube, where sigma is your standard deviation which you saw earlier. Okay. So this is how you can estimate the skewness. Similarly, you have one more term which is called the kurtosis. So kurtosis tells you how heavy the tails are. So that means let's say all of your data is present between 5 and minus 5 for case 1. Yeah. Case 1 and case 2 minus 5 to 5, but there are some points at 10 and some points at minus 10. So this is heavy tailed because there are on the tails at the endings there are some more data points than this. Okay. So this kurtosis tells you how these tails are compared to the actual data, mean data. Now if there is a very large strong tail like these compared to the actual data, then that is heavy tail and it will have positive kurtosis value. And if the data is like this without tails, without much tails, then that is low tail data and it will have negative kurtosis. Okay. And for kurtosis, it is very similar to skewness, but the powers is 4. Okay. So this is how you can estimate the kurtosis. Yeah. So next we looked at if you have a Fourier series expansion of a periodic odd function what terms should it contain, and if you have a periodic even function, we also looked at what terms it should contain, right? So if it's an odd function, if your x data is all negative, then you can just obtain it by negative of the actual function. And if it's an even function, x being negative doesn't change the x the results. Okay. So in odd, f of minus x is minus f of x, and in even, f of minus x is f of x. So we also looked at some examples for this, and we saw how which term should be present. So if you don't remember also, you can derive this on your own and see, to satisfy this condition, that is for odd function f of minus t would be minus f of t, which terms would cause you the difference. So if you have this constant terms, because here you have positive and here you have negative constant. So if the constant is 0, then that means the difference doesn't come. Similarly, for the cos term, here you have positive, here you have negative. So if the cos doesn't exist in your Fourier series, then this also doesn't matter. So in an odd function, only sine terms would be present, and if it is an even function, then you only similarly will have only cos functions. Okay. So this is how you can decide which terms you need in your Fourier expansion based on the type of function you have, odd or even. Okay. And one more thing is, so cos of x, or the cos of minus x is cos of x. So cos itself is an even function, and sine of minus x is equal to minus sine of x. So sine itself is odd. So simply by this also you can see that if your actual function is even, then you should only have even corresponding terms. That means you only should have cos. And if your actual function is sine, odd, then you should only have the sine terms. Okay. Yeah. Next we looked at beating frequency, how you can estimate the beat frequency if you know the frequency of the signals which you actually mix. Okay. And next we looked at when you are digitizing an analog signal, what are the terms that you need to see and what they are called. So one is the sampling interval. So at which time intervals you are actually collecting the data, and the reciprocal of that would be the sampling frequency, and how many data points you collected, that would be the n, and the total time length which you collected the data, that is simply the number of data points into the sampling interval, and the frequency resolution. So the difference between the two frequencies, the resolution which you can actually obtain from such a data acquisition, is just the reciprocal of the total time length, and the maximum frequency that you can obtain from this data is simply n by 2 into the frequency resolution. Okay, this n by 2, because when you do this frequency, you will have some of the data in the half of the data in the negative frequency side and half of the data in the positive frequency side, but you only consider the positive frequency side. So that is why you need to see on n by 2. Okay. Yeah. So yeah. And in real scenarios, actually, not even n by 2, we actually consider n by 2.56 into f. So we actually reduce even more. So if n by 2 would be somewhere here, so you actually reduce even more. Okay. Yeah. So next we have the auto power spectrum, cross power spectrum, and coherence. So the auto power spectrum for a Fourier transform, uh, so it's just the squares on square sum of the squares of the real and imaginary components. So this will tell you the auto power spectrum. And if you are Looking at the cross power spectrum, so this is to tell how two signals are related. So then you need to multiply the real signal of the one with the or the signal with the complex conjugate of the other signal. Okay, so then you will get the cross power spectrum. So the signal into the complex conjugate of the signal. So this is complex conjugate. Okay, yeah. Now there is one more thing called coherence function. So the coherence function tells you how two signals are correlated to each other. So if you have very high coherence, that means the two signals are very well correlated to each other, and very low coherence means the signals are not related at all. Okay, so you can estimate the coherence function from the cross power spectrum and the auto power spectrum using this formula. Okay, and we also estimated for one signal. Yeah. So next have one final question with which we can wrap up this session. So here the mean, RMS, maximum and minimum are given. Okay. Now what will be the crest factor and the form factor? So can anyone tell me? Given the mean, RMS, maximum and minimum, how can you estimate the crest factor and the form factor? Anyone? So the crest factor which we have seen earlier is maximum by RMS, and the form factor is RMS by mean, right? So the crest factor now would be maximum is 15 by RMS is 8.63, and the form factor would be RMS by mean. Mean is given as 5. Okay. So this we have discussed in our first question, and I hopeful that you remember it. So yeah. So this is how you can estimate the crest factor and form factor in terms of the maximum value and the RMS values. Is this clear? And any doubts in the today's session? If you have any doubts, you can ask, and if you want to discuss anything, also you can discuss now. If you don't have any doubts, thank you. Thank you for attending the session. We'll meet again next week. You can log out now. Thank you.